Welcome. In this video, we will be going over 3 main types of organic separatory techniques. So you guessed it, since we called it organic separatory techniques, these are techniques that we're using in order to separate mixtures of compounds based on specific properties that they have. And usually these properties are polarity, charge, boiling point, things of that sort. But if you remember from my aldehydes and ketones videos, polarity and boiling point are actually very related to each other, and so is charge. But we'll still go over these different techniques. So the first technique that we will be discussing is chromatography. So chromatography is the separation based on polarity. So there are multiple different types of chromatography. One of those is thin paper chromatography. You might have done this in organic chemistry lab. So we have thin paper chromatography. So when we are talking about separatory techniques, there is always a mobile phase and there is always a stationary phase. So the mobile phase in thin paper chromatography is our sample. So whatever things that we're trying to separate or try to figure out what their properties are like, that's the mobile phase. And we have a stationary phase, which is a polar adsorbent. So in terms of paper chromatography, we basically have paper. You can also use glass. And this paper is coated with a polar adsorbent. That should be an A. And the polar adsorbent, it's called a stationary phase because it's not moving anywhere. It's on the paper and it's going to stay there. It's not moving anywhere. At the bottom of this paper, we're going to spot it with our samples that we're trying to separate based on polarity. So we're trying to separate our samples based on polarity. And these are what are going to be traveling up this paper plate. So that is why those are called, or that is called the mobile phase. So the way that chromatographies work is that since we have a polar stationary phase, when our sample is polar, so let's say our sample is polar, it is going to want to interact more with that polar adsorbent. So let's say sample 1 is polar. So now sample 1 is going to be really busy interacting with our polar adsorbent. So it's just going to keep interacting. It'll probably only travel up to there because it loves that polar adsorbent so much. Think like dissolves like, always. Polar loves polar. So they're very similar and they want to interact with each other. So sample 1 really wants to interact with that polar adsorbent. Now, say sample 2 is nonpolar. Well, if it's nonpolar, it doesn't really want much to do with that polar adsorbent. It's kind of going to go faster and it's going to travel higher up. So it's going to travel higher up in the plate. So how do we quantify this? What happened to that? So how do we determine which one has a higher polarity? Basically, whichever one travels further. So travels further equals higher polarity because equals lower polarity. Equals lower polarity because it is moving faster. It does not really want to interact with the polar stationary phase. If it's traveling slower, that means more polarity. So it traveled slower and it didn't even make it as far up the plate. So that is more polar because it is really busy interacting with that polar adsorbent. So how do we quantify this? We use something called an RF value. And the RF value is basically a formula, and it is the distance traveled by the sample, so sample distance, divided by the distance traveled by the solvent. And the solvent is our polar adsorbent in this case. So, like we said earlier, if the sample distance is higher, that means that we have lower polarity. And if we have sample distance that's traveled farther than the solvent, that means we also have a greater RF value because the numerator is greater than the denominator. So that gives us a higher RF value, and is the opposite for a lower RF value. So lower RF value equals more polarity. So that's basically what you need to know about thin paper chromatography. Now there's also something called column chromatography. Column chromatography, again, same thing. We have a mixture with two different things, and we're trying to separate those things based on polarity. In this situation, we're going to have a beaker, and we're going to have a column above that beaker. And that column is going to have a stationary phase yet again. And that stationary phase will be polar. And we are going to have the mobile phase. And the mobile phase is going to consist of whatever we're trying to separate. So mobile phase will have our mixture in it. So what is going to travel through and come out here? Well, same thing as before. If we have a polar sample in here, so say we have a polar liquid in here, polar compound, it is not going to travel as fast. It's not going to come out of the flask into here as fast. It's not going to elute as fast. That's because it is too busy stuck here interacting with our polar stationary phase. So it's not going to come through because, once again, like dissolves like attracts like, so polar attracts polar. They're too busy interacting with each other over here. It's not going to come through. But our nonpolar part of the mixture, that's going to travel through very quick because it does not want to interact with the polar phase. It's going to come through. It's not going to be stuck in the stationary polar phase. It's going to come through, and we're going to be able to collect it in our flask. So we just accomplished the same thing. We had a solution up here. We had a solution up here with different polarities, and we're able to separate that and get the nonpolar, compound in our flask and collect it in the end because our stationary phase kind of trapped that polar sample and it was too busy interacting with the polar sample. Now let's talk about distillations. So distillations are basically separation by boiling point. So in distillation, we have a little flask, and we have our flask with our mixture, and our mixture is going to have different compounds of different boiling points. And it's going to travel up this fractional distillation tube, so we can call it a fractionating column. It's going to travel up there. It's going to go through a condenser, and then we're going to collect it here in our receiving flask. So say we have 3 different compounds, and each of those 3 different compounds, so we have 1, 2, and 3, and let's say 1 has a really high boiling point, 3 has a very low boiling point, and the boiling point of 2 is very similar to the boiling point of 1. So how are we going to carry out a distillation? So if we're going to separate by boiling point, the first thing that we need to do is add a flame. So we're going to add heat, and these things are going to start boiling. So here's a point where we should probably discuss volatility. So what is going to boil first? Whatever has the higher volatility is going to boil first. So volatility means we have a higher vapor pressure, which means we are more likely to boil. We want to boil faster, so we have a lower boiling point. And an important definition of boiling point that you should probably know, so I'm going to write it here. Boiling point is basically when the vapor pressure is equivalent to the ambient pressure. So ambient pressure is basically the surrounding atmospheric pressure. So boiling point is when vapor pressure equals ambient pressure. And when we have higher volatility, we have a higher vapor pressure, we want to boil more, so we have a lower boiling point. So if we look at compound 1 over here, we have a higher volatility, and compound 3 has a very low volatility. So when we are boiling, whatever has the higher volatility is going to come out first. And we're going to collect it back in here first. When we travel through this condenser that I mentioned earlier, this condenser has a liquid stationary phase. And that liquid stationary phase over here is just going to basically condense our mobile phase, which is whatever our gas is that is traveling through here. And it's going to condense it back into a liquid, and it is going to be collected here. Now, we also can connect this to a program that shows us what is coming out first. So say we have a peak here, and a peak here in the program. And we have 1, 2, and 3. So it makes, let's actually go 3, 2, 3, 2, 1. So it makes sense that 3 is coming out first over here because 3, we said, has the lowest boiling point, so it's going to come out of here faster. Earlier, excuse me if I said 1, but it should be 3 because since 3 has a lower boiling point, it has a higher volatility, and it is traveling through here faster. So that would make sense that our first peak here is 3, and it would make sense that our last peak is 1 because 1 has the highest boiling point. So just this is another thing to keep in mind. If they kind of give you like a graph looking thing with these different peaks in any question, just know that whatever peak is kind of coming first is the one with the lower boiling point because it's more volatile. It just boiled more. It went into the gas phase faster. So now what is going to happen if we're trying to compare 1 and 2? So now we were able to find the difference between 1 and 3 pretty easily because 1 is has a very high boiling point, which means very low volatility, and 3 has a very low boiling point, which means it has a high volatility. What if 1 and 2 are very similar? Meaning less than 25 degrees Celsius of a difference. So 1 and 3, let's say, have greater than 25 degrees Celsius difference. 1 and 2 have less than 25 degrees Celsius difference. This is where we could use something called fractional distillation. Fractional distillation, it's kind of the same thing, except we are going to have a longer column over here. Longer fractionating column, just to make it more hard for these things to evaporate, and we can separate them a little better. Fractional distillation is used when specifically the boiling point difference between two of our compounds is less than 25 degrees Celsius. Now, another situation I would like to go over is what if something has too low of a boiling point? So what if something is too volatile and it's just kind of evaporating out of there like too fast? We can use a vacuum. That vacuum is going to decrease our ambient pressure, therefore decreasing our vapor pressure, therefore decreasing our volatility, therefore increasing our boiling point. So just another thing to note here that might pop up here and there. And finally, extractions. This is nothing but separation based on acid or base. So this can be separation based on charge, pH, things of that sort. So this setup kind of looks similar to column chromatography, where we're kind of going to have let me draw a little lower. We're going to have a collecting flask, and then we're going to have something above. And our little container above that's going to be dripping into our collecting flask, it's going to have a nonpolar stationary phase and a polar a nonpolar, this is actually not going to be stationary, this is going to be mobile. We're going to have a nonpolar mobile phase, which will make sense because we have a polar stationary phase. So the nonpolar mobile phase is what's going to be able to move past the polar stationary phase and then get collected in our flask because, like I said earlier when we were talking about chromatography, nonpolar is just not going to want to interact with polar as much. So it's kind of just going to flow through. Now, in this situation, our mixture, it's going to have a bunch of different things. It's going to have acids and bases, and we're going to want to separate that. So we're going to want to separate that and just collect what we want in this flask. So if we want a base, we only want to collect the base. If we want acid, if we just want the weak acid of our solution, of our mixture, that is what we want to do. And the way we do that is through adding different things through here. So we're going to add acids, bases, they can be weak or strong based on what composition we have in here. So if we have a weak base in here, we can add a weak acid, and that's going to protonate that base, and then it's going to become polar, and then it can come through here. So we just need to base it off of what our solution has in it, and then we can add new acids and bases, weak or strong, into what we have currently so that we can get what we want to travel through the polar stationary phase and then collect it in our collecting flask. So there you have it. That's a basic overview of organic separatory techniques. There we go. It's clearer now. Organic separatory techniques. I hope that was helpful.